Good afternoon, good morning, good evening. Welcome, Smiles. Many Prime here. We back in another teaching video. Today, remember in the last episode that we were learning about graph theory and all that? Well, that was the start, okay? We're going to be moving on to a new set of mathematics. However, the graph theory from last time is linked because there is an analogous thing that it makes more sense. So this time we're going to be looking at a new completely automatic new mathematics called finite state machine automata. I think it's automata. I think it's called let me see. It's it's actually called formal languages and finite automata. Now, in simplicity, yeah, I did the first letters because okay. In simplicity, this is a this is a branch of mathematics that involves a model of computation with input data acting as a machine. This is the essence of mathematics here. If you think computer science, we collect bits, say 0011. We collect 4 bits. It's a nibble, but that's for another day. The nibble is what we call 4 bytes nibble. If you collect these 4 bits, you can collect it using these states, where you can have a state called Q0. You send a 0, it stores the 0. You have another state, Q1, Q2. These are the conventions of what they say. 0, 1, and then maybe no, Q4. One. This is a convention. They store input data as okay. Yeah, I know I'm saying a lot of stuff. I'm just talking to you about the overview. We're gonna be talking about finite state automata, okay, which is about collecting input data as a machine. Today is the introduction because there's going to be more of them. You're going to see double upload tomorrow if the likes are there, if the views are there, okay? I'm telling you, this is a very good topic. It gets super complicated, but the journey will keep continuing, okay? Because I'm going to be teaching automatically, hopefully anyway, okay? So what we're going to start off with is understanding what finite state automata is. It's linked to graph theory. We can do an analogy with this because we understand that this is a computation. We'll look at the individual parts, the states, language, alphabet, input strings, which is what you can do, and maybe another example. Okay, so without further ado, I think we understand that we can continue with it. Also, you see the new setup. You see I'm evolving the new setup because last time we were on the floor and that was not very helpful. So let's talk about what a finite state automata is. I think this is finite state machine or automata. I think the automata is an abstraction of a machine. It's the simplified way to computation with a machine. So they essentially mean the same thing. If not, the comment section is there. You can inform me. I'm still learning. This is new. It's a mathematical model to represent computations. And usually we do this by having these things called states, and conventionally we state the states as Q0, Q1, Q2, and so forth, for Qn, where n is just a number. You could say Q9 is, and n is 9. So we have these states Q0, Q1, 2. We have these states, and then we have these things that are called transitions, and they go from one state to another. From that, you see this one is double circled. We'll look at the terminology in a little while. This is similar to graph theory because graph theory, this would be a directed graph because you have arrows. You have one-way arrows. You can go from here to here, but you can't go from there to there. The directed graph. I don't know if I talked about the directed graph in the last episode, but you know what a graph is. These can act as vertices, and these are edges, directed edges. So we already know. This is an example of what we call an NFA, a DFA, but it's also how you represent these finite state machine automata. Because this is essentially what happens. You send a value, say maybe a number or a letter, let's say numbers. Send a value, this gets computed, so the number one is added. You send another number, and then you send another number, and that's essentially the abstraction for this. We can think of this as we can think of this as a road. Okay, these are one-way roads, because you can go from here to here. This is a place, maybe your house, for example. This is, you start off with this, a place, your house, and then you go to maybe your school. You go to school, so you go from your house to a school on a one-way road. You cannot go back, and that is how you get here. Because yeah, essentially you can model this as graph theory. They're not the same thing. Essentially you can think of it as a road. These are roads. Then the formal definition of it is a transition. Oh no, that's the name of it, but they essentially mean the same thing, because they're just analogies. Now let's look at the terminology, because you're thinking, what am I saying? It doesn't make any sense. So let's redraw this graph. No. Okay, so we have here an example of a graph. We can say we can say DFA, NFA. Those are names that we will look at later on, because we're just looking at the terminology. This is the structure you will see for a finite state machine. Now we have, so these are the terminology that we use to describe this. There's a start state, is an accepting state. There is alphabet, and I think that's really, oh yeah, and transitions that we talked about before. Transitions. The transitions are these edges here. So let's talk about the start state. You know what the word start means. The start means the start of something new. It's the beginning. Now, the beginning means before we compute anything, we need a starting point, a beginning point, so that we can move to collect the data that we want, essentially the ones and zeros, and then finish off and collect and accept it. So the starting point is where we start from, and that's denoted by this arrow, because the arrow is indicating we want to start there. That's why the arrow's there. So that's the start state. The accepting state is the state where there's two circles around it. Yeah, this is a bit long. It should be around here. No, close. So this is the accepting state. You can think of this as a target in the bullseye, because do you know how there's bullseye here, and then you can shoot it. If you shoot a dart here, you get a score. Say this is 6. You get a score of 6, and then this is recorded. That's your score that you get. So I think of it, if you get a transition, get the 1 there, but now you put that on the dartboard, so you record that. Essentially, that's where you can end. But But it won't end if you just touch it. It can end when you want it to end, and we will see shortly how that is the case. The alphabet. You know what the alphabet is? You've spoke the alphabet. You learned the alphabet. This English I'm speaking right now, it came from the alphabet A, B, C, D, E, F. What's this? A set of elements or letters that we use in life. Here, the alphabet is the set of these values 1 0. They are only 1 0s because those are the different unique ones. And then you can make computations from it. You can collect you can do 1 0 1. You can make things up like this, such as how in the alphabet you can make words up. Bad, you can say it goes B A D because it uses the letters BAD, bad, to do that. So that's what the alphabet is. The alphabet is the list of the elements, numbers, alphabet, whatever you could say, that are used in your diagram. Now, I think that's mostly all of the terminology you need for it. We talked about states, we talked about the automata, we talked about the alphabet. Oh yeah, the language. Language comes from the alphabet. Language comes from the alphabet. They are directly related, equals whatever you want to do. Alphabet. In English, alphabet A, B, C, D, all the way to Z. Language is the words that are approved in the English language Oxford Dictionary. You can name it all. You can name it all. I can see that. Okay, let's say a word, pencil. Okay, because I have a pencil right here. Okay, pencil. They have each of the 6 letters that are in the alphabet, possible alphabet you can use, and this is a legitimate word in the language. So here, a language means the set. Well, let's do another page. The language is the set, which means the total amount of. No, it means anything that includes it, or the set. For a Venn diagram, if something is in here, if there's A, this is the set of everything that can be an A, for example. Yeah, okay, a set of all possible combinations of the alphabet. That's what the literal definition means. So the definition is that you can have the total amount of words, the total possible amount of combinations that you can make from the alphabet. Same as how the Oxford Dictionary has probably all the words that the alphabet can make in English. I haven't read the Oxford Dictionary fully. If you want to see that, you already know what to do with the like button. Okay, so there's a formal definition to define finite automata. And we can say this is a 5-tuple. We don't know. Do you know what tuple means? I don't really know. It's a data structure, but we can call them elements. Let's say elements for now. And you will now have seen some of these elements. I see you. I know. I'm the same. I don't like elements. But guess what they say in mathematics? Mathematics is a language spoken in words, written in symbols. When you understand the words, you understand the symbols. It comes words first. Well, let's write that. Words first, then symbols. You need words and then symbols. Okay, so so each of them we has a number. Each of them has a definition to it. So the Q is just the states. How we talked about here, where there were states at the start and at the end. These are just what Q represents. Q represents the states. Sigma, this is what you call it. Not that sigma, I don't do that stuff with. It is the alphabet. We already talked about the alphabet. I think this is, no, that's not epsilon. Let's call it unknown. Unknown is the transitions, because the transitions, the edges that we connected from each of the circles. We have Q naught, or you can say Q sub 0. No, okay, is the start, because conventionally it goes from Q0 to Q1 to Q2, etc., etc. And then P is the accepting state. That's when, and that's when it decides to stop. That's when the machine will, not the machine, the computation will end and the result is given out. Okay, so we understand the terminology. Now this is new for this episode. Okay, I actually have a question ready for us to tackle, because I'm on it. I'm oh, my pen fell down, because I'm on it. I'm trying to evolve the learning so you can get the most benefit out of it. We have a question from the textbook itself, the exercises on 1.1. Now there's lots of these, so this is a series. Okay, we'll talk about this later, the episodes, but I think now we can work out the first starting question. So what I'm going to do is I'm going to draw M1 and M2 out so that it's clear what it is. So just give me a few moments while I do that. Okay, I'm done. We've made the diagrams. We understand now. It took time because constructing is hard. Plus I made some errors. You can take me for that. Okay, I'm here. We're going to answer a question. This is so fun. Okay, we can answer a question. The first question is, what is the start state? Part A says the start state. Remember, the start is the start. We begin the state to, we haven't collected anything yet. This is the beginning. What did we say was visible in the beginning? We need an arrow, okay? So in M1, we are looking for the state that has an arrow, and that is Q1. So Q1 is the start state for M1, and in M2, the arrow is in Q1. Again, as a normal. And yes, you do see that the accepting state is in the start state. That is allowed because each state can be accepted. You can accept nothing, and that's fine. We will talk about the nothing a little bit later because it says it in the question. Okay, part B. What is the set of accept states? Okay, the set means the total possible set states. In M1, we said the set state was the target circle, and that is Q2. So Q2 is the accept. But do you notice that in M2, there are two accept states here and here because of the target thing around it? It's not ironic, the two with the two. Yeah, okay, it might have given it in the diagram itself, but here the accept states are Q1 and Q4. We put comma because it represents the next one as well, because as a list sort of. So that's A and B done. We are doing very well with exercise 1.1. We are doing good. Okay, Part C. What sequence of states does the machine go through on input AABB? Okay, we did not talk about the input AABB, but this is this is not that hard to explain. Okay, so it says input AABB. What do we mean by this? Okay, so we put an input. You can say an input is something that wants an output. If we have an input, it means output. We start off with a 5, we input the 5, and the process says times 2, and then we output a 10. The input and something happens, the output. This is a function, but I'm just saying the input is just a value that is at the start. That's not a really good example. Okay, input. This is traversal. Okay, you see A's and B's here. That means that when we go from here to here, we say A. We have an A. We go from here to here, or which in A we can say AA. We can do AA. This is saying that we want to do A, B, B, and we want to work out the sequence of states. So we want to see what state does it go to. Okay, so let me give you an example for M1 AABB. Okay, we start off with Q1 because that's the start state. We do an A, so we go to the state where you can allow an A to go through. So that's this one because A is here. A is the value that you can go to here. So that's A done. Then we want another A. So from Q2, we can go to Q3 by this A. You can't go through this A because this A can only happen from here to here since the arrow is this way. So we can go to Q2, this A, and Q3. So B, now we need a B. We need to go from Q3 to Q1 because that's the direction that a B is allowed. And then the last one, B, we can go from Q1 and then we can loop around with the B. Okay, so then the set of states is Q1, Q2, Q3, and Q1 because we went A, B, B. That is the step-by-step how we do it. It's a traversal. We follow it through. I need to go to A. No, I need A. I need A. I need B. I need B. Okay? We understand. And this is the same for M2. So A, B, B. We can do this again. We start with Q1. We go to A. So which arrow has an A? This one, so we go this way. We need another A, so we go this way. We need a B, so we go this, and then we need another B. I forgot to label this one B. Need a B, which goes here. So the sequence of states, you just have to list which states has been seen. These three. This one hasn't because we haven't gone from a state to here because we didn't see it. That's why this is not on here. If you understand that. Now, it says here for part D, does the machine accept the string AABB? This means that does the string end up in, does the last one, when you go through a transition, when you do the last transition, does it end up in the accepting state? Because the accepting state will accept the input or the string. And here we ended up in Q1, and Q1 is not the target circle. So that is no. In Q4, no, in M2, we end up in Q4. Q4 is the target. So that's a yes. So we can accept this string on M2. Last one, does the machine accept the string epsilon? Okay, so let me, actually I can continue here. I will do it here. Epsilon, this is the Greek letter epsilon. This means empty. empty input string. Empty means there's nothing there. There's no elements, no input, no power. So that's what the empty thing is. It says, does the machine accept the string epsilon? So if you input nothing, which is essentially just the start, you don't go to any transitions, then will it accept it? This means that in the starting state, it will just stay in that state and not move. So it will only accept the epsilon string if the starting state is an accepting state. Because if it's the accepting state, you can bring in nothing because it can't go A is not empty, B is not empty. It can only be nothing and then it can be nothing and then it can be accepted. But Q1 is not the target circle, so that's not going to work. M1 is not going to work. However, M2, the starting state is the accepting state because it's the target circle. So epsilon will be accepted for M2. And that is very good. That is triple tick good because it does. Okay. Wow. We just did exercise 1.1 on the DFAs. We'll talk about what DFA means a little bit later in another video. We just wanted to talk about the brief overview on the terminology. I know I didn't explain it the best. I just tried to make an example. Maybe it needs to be a little bit more clear, but hopefully you enjoyed and you understand everything. What we went through is the finite automata. We know the simpler definition. We know what a language means, what each of these words means, and that's mainly the starting point, the fundamental point. And with that, we can start doing fun stuff with this new ultimate piece of mathematics. If you want to see the series, you know what to do with the like button. I'm trying to get double upload tomorrow because this topic is very fun. I know explanation wise it's still learning because I'm still learning how to explain it, but hopefully it helped you anyway, because if you don't understand the fundamentals, you can't understand the later stuff in the topic. So thank you very much. Hope to see you next time for more explanation. Not on the floor, just on here, because this is a good place. Thank you.